All right, so I think hopefully that's been enough time to reflect on where you are in terms of deficit in learning or knowing something that you feel like you should know, and then maybe figuring out a little self-reflection, like what have you done that maybe could benefit you if you do it more often, and then also you know where you are. I did go ahead and add, because some of you guys said you struggled with the steps, like how to frame the steps. I have more copies of this, but I know not everybody needs this. This is an extra structure that you can utilize today to help you organize your thoughts and organize your process, because everything here is process oriented. We're not so end oriented. We're not so solution oriented. Yeah, I put the answers in the board. That's because it helps you know if the process is correct. Yeah, I'm talking about. So this is a little guide that says, okay, step 1, balance chemical equation. Isn't that what we said the first step always was for any kind of stoichiometry process? Okay, cool. Step 2. Okay, so do step 1, right? Step 2, identify the known and unknown, or the given and the unknown, and then arrange the steps given and get the given to moles, and then so forth. Get your unknown, and then get to the unit of interest. So I'm going to leave these at the desk because some of you guys may really like that. And at the front, that gives a lot of guidance. In the back, it's just a little bit more blank. And since we're going to be solving some problems today, there's probably enough for 4 questions on there. It may be an extra structure that's really helpful until you get to the point where you're like, I can do this by myself. Okay? So we're going to start with number 4, which was the last one on your practice. So you guys should be able to tell me first the balance chemical equation. Go for it. Sodium sulfate is what? Na what? Na2SO4. Okay, so sodium sulfate, Na2SO4, because 2 comes from sulfate's charge. Okay, barium nitrate, Ba, NO3, 2 yields. What kind of reaction is this? Double replacement. Sodium gets with? No, sodium gets with nitrate, NaNO3, and barium gets with sulfate. Okay, so go ahead and if you start reading part A, you're like, oh, precipitate. So there must be a precipitate that must be formed. So have your blue sheet out for precipitate rules or for solubility rules. Additionally, we have to balance this. So I've already given you guys the answers on the balancing part of this, and this is old news. So we see the 2 nitrates and 2 sodium, so we must have 2 sodium nitrates over here. That is a 2. Okay, and so we're looking at sulfates. Look at your rules for sulfates. What's it say about them? All sulfates are they're soluble except for what? Barium and a couple of other things, right? Okay, so all sulfates are soluble except for barium and like calcium and mercury and strontium, I believe, right? So sulfate is aqueous. And this sulfate is a precipitate, so I'm going to write a little arrow down to indicate that. And then barium nitrate, all nitrates, doesn't matter what it's paired with, is what? Aqueous, so they're all soluble. Okay, so those given rules to you are there because they don't expect you to memorize everything. They just want you to know how to use a tool. All right, so balance chemical equation done. Step 2, identify unknown and the givens. So this is a weird situation because it gives you 2 pieces of information, but they're used collectively together always. So molarity, which is that big capital M, what does molarity mean again? It means solution concentration, but it has 2 units. It's like a fraction. Molarity, moles per liters, right? Moles per liter. Now, remember liters being in 2 ways, or they were represented in 2 different ways. Liters of a gas, which is 22.4 liters per mole, and then these like little milliliter liters, which is just a solution, like a liquid solution. So when you're talking about gases, you're thinking 22.4. But when you're talking about solutions, remember, do not use 22.4 because it is not a gas. So we actually have to recognize that this is a different kind of unit. Okay, so I told you guys last week as well, write this down for yourself if you didn't. M times V will always give you moles. M as in molarity times V as in volume in liter form will always give you moles. Because what's molarity? One more time. Moles over liters. And if I take moles over liters and I multiply it by liters, what do I get? Yeah, the liters cancel and they give us moles. So that's why I think it's really nice when they get you together because you know that you should be multiplying those. The only thing that's weird is you can't quite multiply this yet because this is in what? Milliliters, and I must get it to liters to actually show that cancellation of unit. So I know I'm going to have to do something with this as a given. So even you guys were even writing down given like one like this, which is great because it helps you identify the most important pieces of this of the problem. So this is molarity of what though? What solution? Sodium sulfate, Na2SO4. Okay, how many grams of precipitate will form? So because we're smart and we already determined our precipitate, what is this actually asking for? Yes, grams of BaSO4. That's what it wants to know. And so you had to kind of read between lines and what that was representing. Now, to actually begin, I'm going to start us off with M times V. But does it matter if I say M times V or V times M? No, it's going to give me moles, right? So I'm going to go ahead and take my 120 milliliters. Can you just take that in your head to liters? Say again? 0.12. So when you take 120 and you divide it by 1,000, which is how many milliliters in a liter, you back the decimal at 3 places. So that's 0.1200 liters times my molarity. But break my molarity into the two pieces it actually is. What is this supposed to be representing? 0.01 what? Moles of what? Sodium sulfate, I hear it. Okay, over what? The liter. Correct. So at this point, what units will cancel? The liters will cancel. Okay, so I'm in moles. Mole is the easiest thing to get anywhere from because that mole is going to connect us to either, well, actually, this is moles of X. We want to get to moles of Y, which is, in this case, is who? The barium sulfate guy, right? So on your mole map, you're at moles of X. You're getting to moles of Y. How do you get between the two moles? Mole ratio. So where do we get that information from? From the coefficients from the balanced chemical equation. Great. So who am I looking at? Which two pieces? So one of the sodium sulfates and one of the barium sulfate. Now, I know you're thinking 1 over 1 doesn't change my number at all. But that process makes you think about what are you talking about? What number doesn't matter necessarily, but what the identity does matter. So we do have to show the cancellation of units for moles of sodium sulfate. Goes on top or bottom? Bottom, because the mole of sodium has gone bottom. And the 1 mole of barium sulfate goes on top. So this is a necessary step because it gets me out of apples into oranges, or from X to Y. And this is from the balanced chemical equation. Because if I never change to moles of barium sulfate, I'll never actually be able to get the grams of it because the masses do differ. So at this point, I need to get from where I am to my final answer, grams of barium sulfate. So what do I need to do here? Right, calculate the mass of each of these. So what number goes in the bottom though? 1 what? 1 mole. 1 mole of barium sulfate goes on bottom because I need to cancel the moles of barium sulfate out because your unit on the top always guides you to the next bottom one. The unit on top always guides you to the next bottom one. The unit on top always guides you to the next bottom one. And so the grams of barium sulfate will go up here, but that's our molar mass, which is, anybody? 233? 233.39, something around that. So a pretty large number. Barium sulfate is heavy. So everything has canceled except for what unit? The grams of barium sulfate. And that's our final point here. So that's our unknown. Go ahead and calculate for me. Practice your calculation. Any takers? Yeah, Omar. 0.28 grams, that's it. And just the nature of calculating it helps you make sure that you're putting things in the calculator right, because I wouldn't want that to be your downfall. So double check that with yourself. And that one will have 2 sig figs because of the molarity having how many sig figs? 2. This one only has 2 sig figs in it. This one has like 4. Everything else, like this is a ratio, not a measurement. This is always going to have a lot, usually, because we have a pretty dang good periodic table. So in this case, it's 2 sig figs. Good point. I always check the givens. Yeah, the givens are usually where I derive those from. Yes.
So you don't look
In that case, you still would only have 2 sig figs when you multiply. You get 120 milliliters or point. Basically, when you multiply them, it should be 0.12, but I always keep everything out because I don't want to cause rounding error in between a problem. Okay. All right. So that one was a straightforward one because we were able to get to moles very quickly in the beginning, and once we're to moles of one thing, how do we get to moles of anything else? Mole ratio. And once I'm in moles of that other thing, I already know my 3 mole relationships if I wanted to get to grams, to atoms, or to liters. Now, this one's going to act a little differently because the question's not about one of those 3 things we know. It actually makes us reference this fraction, this conversion factor, and think about what all fractions or all conversion factors can do. If you want to flip it, can you flip a fraction? Yeah, you can flip anything because it's all about you canceling units and making sure you're writing them just correctly. So that's likely what we're going to have to do here. All right, so when 50 milliliters of 0.1 molar sodium sulfate reacts, how many milliliters? So we've never been asked for the milliliters yet. Now that's the only thing that's different. 0.1 molar barium nitrate will be needed to react completely. All right, so we have 3 numbers here, right? Which ones seem to go together? The ones I've underlined here go together. And what can I do with these? I can do the thing. What's the thing? I can do, what can I get to? What unit can I get to that's so helpful? I can get to liter and then get to moles, because I can do m times v to give me moles. I can do that up front right here. But at the end, it gives me another molarity. So I'm going to save that because I know that's going to be actually used at the end, and I'll tell you why. It's because this milliliter is going to be referencing this concentration. So I'm going to have to use that molarity conversion factor at the very end. So let's get there first, okay? So how many liters is this? 0.123, yes, 0.0500 liters. So I'm doing liters times, what's this molarity thing mean again, fraction-wise? Put the numbers where they go. 0.01 moles of sodium sulfate. Yeah, make sure you're identifying as you go because then you won't get lost. And that's always per what? Per 1 liter, right. So whenever you're doing your molarity, and this is the refresher for Friday as well, the number that's in the front of the molarity is regarding the moles, and it's always per 1 liter, and that helps you not mess up what you're writing the 1 with and so forth. So at this point, hey guys, basically I'm the moles, right? So I've gotten my liters taken care of. Liters are out of the way. I'm in moles of sodium sulfate. Who cares about sodium sulfate? Who do we want to get to? We want to get to barium nitrate. So I didn't actually write down my given in my question, sorry. I want to get to barium nitrate. That's my question. So get me from moles of sodium sulfate to barium nitrate. Where are you getting your ratios from? Balanced-Chemical equation. So what is my ratio here? 1 what? On the bottom? So moles of sodium sulfate, guys, you tell you what goes on bottom. So mole of sodium sulfate here, and this 1 came from the 1 up here, okay? And then what goes on top? And what number? 1 as well. Barium nitrate is this guy right here, has a 1 as well. So there's 1 mole of barium nitrate here. Beautiful. Okay, so now I'm out of the apples and into the oranges, or I'm from X to Y. I'm at barium nitrate now. So this is the weird part. My liters have canceled. My moles of sodium sulfate have canceled. I gotta figure out how to cancel moles of barium nitrate to get to milliliters. Well, let's just say ignore milliliters for a second. Can I get to liters?
Yep.
Yes, and I can easily, if I get to liters, I can get to milliliters without a doubt. It's just 1,000 is our multiplier. So let's just call this question liters of barium nitrate. I have moles. What's the relationship between moles and liters? Don't say it.
Oh.
That's only for a gas. I knew you were going to say it, so that's why I asked. It's not 22.4. There's another relationship on the board, but we just have to identify it as a relationship. What are you going to say, Ishmael? Well, those together give me moles, but also I have this nice conversion factor. If I have molarity, I already have the relationship between moles and liters. It's different every single time because concentrations differ. Really concentrated might be 15 molar. Really dilute might be something like this, 0.01 molar. That is the relationship right there. So, what does that actually mean? What's it mean? Whatever what? Okay, hold on. Let me write it out first as 0.010 molar. What's that mean in terms of number of moles? That number of moles over 1 liter. And then what you'll notice is if I put this right next to this, will that cancel moles? No, but what can I do? Flip it. And the moles will cancel. Okay, so that is your relationship. So make sure you're looking in text at this question because the liters for gases is totally different than the liters for a solution. So this gets canceled by writing this, but flipped. So the moles has this number with it. You have to write that number with it. 1. And why am I putting it on the bottom? To cancel out moles of barium nitrate from here and here. And that liter is the thing that goes on top. So I flip my fraction. I'm just going to put liter solution just to identify what I'm talking about. Not a gas, it's a solution. So I'm almost to the end. The final question was actually milliliters, if you remember. So how do I get from liters to milliliters? What goes on top? 1,000 milliliters is equivalent to 1 liter. And so the moles of barium nitrate canceled with this up here, top and bottom, liters, and I have my end point, which is 50? Yeah? 50 milliliters? Is that right? I'm just making sure my mental math is there. Yeah. Okay. Now, I'm going to be honest. You have some logic about you. This actually can work itself out if you look at the proportions in which they react. Can I scroll up just a tad from here? Yeah. Okay. So how do they react? They react in a what ratio? This is sodium sulfate and barium nitrate. 1-to-1 ratio, right? So if they react in a 1-to-1 ratio and the concentration of sodium sulfate was 0.1 or 0.01 and the concentration of barium nitrate was 0.01, they needed equal amounts of both of them to fully react, to stoichiometrically react. So they react in the correct ratios or the correct amounts. So that was a funny one because that kind of confirmed your finding of logic, but that's the power of reflecting on your answer. Like, does it make sense? Heck yeah, it makes sense. It's a 1-to-1 ratio, it's the same day concentration, 50-50 mix. And so that's why that endpoint of reflection is kind of helpful at the beginning because it gives you a little pat on the back. Okay? Let's do one more here. This is our last one on the part on number 4. So 2.5 moles of precipitate. Notice it's very cryptic, right? I don't want to tell you who the precipitate is because it requires you to think back to your solubility rules. Who's the precipitate? Okay, so that's my what here? Given or unknown? That's truly my given. Okay, so my given information is 2.5 moles of barium sulfate. And you guys have your Balanced chemical equations right on the top of your paper. I'm not quite sure what some of you guys are working through it with me and some of you aren't. So when I take this up, I hope that you've written it down for yourself. So we have our given of our precipitate. How many grams of the other product will be formed? Again, very cryptic, but we can figure that out. Who's the other product? Sodium nitrate, right? And you guys have that on the top of the board where you have your Balanced chemical equation. So this is our unknown. So I've got to get from moles of barium sulfate to grams of barium sulfate to grams of sodium nitrate. So before I begin, where am I at on my mole map? I'm not moles of that. I'm not moles of the first thing. I'm halfway there. What do I have to do first? So the ratio to get to the moles of the other thing, which is sodium nitrate, right? And then what? And that's it, right? Molar mass is what you mean by that, right?
Yes.
So how many steps is this one?
2.
2. This one's an easy one. The middle one is the only one I really thought you guys were like, what in the world are we doing in low? But this is normal stuff right here. So 2.5 moles is what I start with. Moles of barium sulfate. You guys just told me what was the next step. Mole ratio. So you give me that because I don't have my balance chemical equation is hidden. What goes on the bottom? 1. Okay, so 1 mole of barium sulfate, and that's from the coefficient, right? Of the balance chemical equation. And this had a 2 with it, right? So 2 moles of sodium nitrate, as it was said on the balance chemical equation. So the moles of barium sulfate cancel with this one, and we always orient it that way to cancel the units as we go. Now I'm in moles of sodium nitrate. Sorry, I'm in moles of sodium nitrate. I want to get to grams of sodium nitrate. And you go back and think about your mole relationships. You know there's a single step between those. That's your molar mass. What goes on the bottom? Yes, we always write 1 mole unless we're considering coefficients from the balance chemical equation. Every other time, though, we write 1 mole. And what's the mass of that? What is it? 95? 85 grams. I'm guessing like 0.0. Okay. And that is our final moles of sodium nitrate cancel. We're in grams of sodium nitrate. So we're to our final destination, and we calculate. So 5, so like 425? Okay. And we likely would have to do 2 sig figs. What would 425 be rounded to 2 sig figs? Say again? 10 to the second. So 4.3 times 10 to the second, or just 430. You could round that to 430, no decimal, and that would still give you 2 sig figs. I may not have had the correct sig figs on my first answer beginning of the day here. Alright, so other than the molarity one, which was a little bit of a new idea, but it drastically contrasts between the liters of a gas and liters of a solution. Do you feel a little bit more distinguished with those 2 facts? Gases are 22.4, liters of solution is this molarity stuff. Okay, the other stuff, 1 through 3, I know a couple of you guys need some help on, and some of you guys need to probably just some time with someone who knows what they're doing. So how about any of the other ones, 1 through 3, I can maybe get you started on. Frank.
Can you go 2C?
2C, yes. That was silicon dioxide. Okay, so first off, what was your balance chemical equation? Silicon dioxide reacts with?
It was into carbon.
Reacts with carbon to yield. So we've gotten these 2.
Yield. Silicon monocarbide.
Okay, so monocarbide means 1 carbon, that's why we have 1 there. Carbon monoxide, 1 oxygen, that's why we have 1 there. I already bring the clearances to you at this point. And then we needed to balance it, and I believe I balanced this for you already on my work that I had on the very beginning of the day here. That should be balanced. Yes. Okay. So on part C, I'm going to just scroll down a tad. So part C, the question was how many atoms of oxygen will be produced. Now, you have to realize that this atoms of oxygen being produced is actually embedded in what? Look at the products. So it says oxygen being produced. So look at the products, and where is the oxygen at? It's inside of carbon monoxide. So we're going to have to think about how to go from carbon monoxide to just plain old oxygen at the very end. So that was kind of like our Reese cup or Reese package, and then inside the hamburger cup store there. We'll look at that here in a second. If 4.6 moles of silicon dioxide react completely. So 4.6 moles of silicon dioxide is what I'm starting with. That's my given. I'm writing everywhere here, sorry, but that's my given. And I know I'm already in moles, right? I'm halfway there. So which of my products am I actually trying to get to? Say again? Carbon monoxide. So I know that I really am looking at the oxygen inside of carbon monoxide. So what was my conversion between silicon dioxide and carbon monoxide? 2 to 1, right? So I'm putting the 2 on top. Why? Carbon monoxide, and I want to get rid of silicon dioxide. So these numbers are from the balanced chemical equation. All right, so then I'm in from moles to moles of carbon monoxide. And then I told you guys something about an internal mole ratio at one point in time, and that's kind of what we're looking at, but I'm going to go with the flow of what you guys think I should do first. If I'm at moles of carbon dioxide and I want to get to singular atoms later, say again? I got to use the particle conversion because I got to get to the smallest thing I can, which in this case is what particle? Well, what's the name of the particle of that? Well, no, particle name like molecules, formula units, or atoms. That is I heard it. Why is this a molecule? Because it's covalent, it's 2 nonmetals. So I want to cancel, put moles in the bottom, so mole CO in the bottom, and that is going to get me to 6.022 times 10 to the 23rd molecules of CO, of carbon monoxide. So my moles of silicon dioxide cancel, and my moles of carbon monoxide cancel, and I'm in molecules. I'm in singular little guys molecules, and they look like this, like something like that. Okay, so that's what it looks like. How many atoms of oxygen are inside? Just one, right there, 1. So inside of the carbon monoxide, there's a 1 subgroup next to the O. So I need to put 1 on the bottom here. Whoa, goes on the bottom. What's the name of it though? Molecule. 1 molecule of CO has what inside? 1 atom of oxygen. Good. That was the last funny stuff and we went over our quest quite a bit last week, so that was like number 3 on the quest where you guys were going from like magnesium phosphide to just magnesium atoms. Similar story here. So everything cancels except for atoms. So that should be 5.54 times 10 to the 24th atoms. All right, give me a thumbs up if you feel like you're able to proceed in terms of finishing what you need to finish. Okay, a couple of us are about half and half here. All right, so here's what I'll do. I have a little bit more to talk to you about with percent yield. It's probably going to be 15 minutes, but I'm going to save it for a little while. So if you are done with your practice lecture problems 1 through 4, I want to see those. I'm going to stand back here so I can check you guys off. And then you guys go and start your problem set 12 underneath the same unit packet that we've been working with for like 2 weeks. So if you are done with practice 1 through 4, you are going to look at problem set 12 and begin some of these. I'm asking for 4 to be done tonight. So I said start on what you could this weekend, but you guys are probably struggling with this. So go ahead and work on that for about 15 minutes right now. If you need to grab a laptop, and you guys know that starting Wednesday, we lose Wi-Fi. So you'll lose your data, and I'm not sure how good my signal is in here, so I'd start being really nice to my laptops. Okay, so I'm going to scooch back there. Otherwise, you guys sit at your desk and work. I'll come around for help when I can. Use your notes. If I leave this right here, you might even be able to see it decently, guys. Okay, Mikado, give me a second. If you are done with 1 through 4, come back to the lab station and show me.
I'll just say like people, but
Yeah, those ones that
yeah.
That's why okay, that's why I had them there. Hold on. If I give you that, is that good?
Yeah, thank you.
Oh, I had 500. That was supposed to be 50 before.
So what was your gift? So for like the formula, which is not always like, it's not balanced, in the balance.
Yes.
Like the two beats, it's only 2 liters of carbon dioxide.
Still in that class, yeah.
Actually, yeah. What's your
Use the 25th and 48th. What do you mean? For like the second step.
Guys, usually much means mass. Much means mass. That's a kind of behind the scenes term.
like say 22.4?
How much
Just metal
carbon is reactive? But would you still
hydroxide has a much lower aluminum to
much means
no, three.
So it's hard sometimes you're like, if I come with a carbon inside of another product or another addition, it says reactive, so if you're not would you give it a description? Much means massive. So this would all be 2 moles.
So do you put 3 carbons or just 1
So if you have to multiply how much is
Would it be 1 mole over 1 million?
unless it was a solution, you won't use that. You won't use that. You have 6 solutions. Alright, so what you got?
Like, for your final step, just 1 carbon.
I think with the mole ratio, how much?
Oh wait, no, I was looking for water portion. That's not important. It's just a given question. The given are the 98 pounds. That's a given. and you're converting to what was the other side? The product. No, the conversion to product. Exactly how much is the product. So it's aluminum hydroxide. That's what it's called. So you're at one mole of L2 equals 3. There you go. You're going to just make sure you ask what number is this? 3A. Oh, exactly. I don't know. Forget that. Yeah. I was looking at 2. What were you trying to find out? That's the only one I got right. Like that's like 4D. I got 24. 1D. 45.6. Not chloride, chloride. How did I get 14.7 for B? 24. Alright. Killing all my
Remember, afterwards, we start on concept 12. I'm helping a couple of individuals, so I'm making my way.
How would you set up G equals C? Number one. And that's on the bottom? Okay.
And then let's try that by 3 moles of 2 ounces over 2 moles of
Yeah.
and then we'll try that by
How much water? And that's 29. See? Oh no, I screwed up this. So 122.55.
Yeah.
Do we calculate molar ratio on it?
she still has to show her. You like,
Yeah, okay, so I did 67.2.
I think I'm good in the process. It's just I can't calculate. That's why I'm trying to do like, you get how like the yeah. Do you like circle back on the math? The problem is that most of it.
Figure out how to get the
Computer. We're looking for a project. Okay, when I will not do that. When we're done, I want to try to. Yeah. For 3C, it says, yes, it says when 67.2 grams of aluminum oxide react completely. So, like, what are you trying to, like, find out? 67.2. Yeah. Oh, okay. That's not what you did. The aluminum hydroxide, yeah. If it asks for product, it's always going to be on the right.
Raise your hand if you're working on your process. Thank you. Okay, wait on me. Just keep rolling. Don't wait on me. Okay. Thumbs up.
Text this last name. Oh yeah. She wasn't here yesterday. Her father, right? So we were here editing the library.
I turn you for that.
How many of those? How much is a lot? Like quantify that for me.
Probably like 24.
Such a more than a period missing late. Please.
I remember I turned on one milk line, and I would be out of the period at the end.
She thought when I wrote impact, I was writing the so it was 4 parts out of 15. I like it all, but I don't know. I like her. Ready to check.
Yeah.
Which one? How'd you start it?
To 1. You don't have a crossword, so you're not doing a crossword right now.
Alright, working, what you found on the board for me, we're only gonna do one of these problems today. We'll do one for tomorrow. So weird, anyway, it's not on my phone. Because of the length for it.
Okay. So this was based off a tiny definition you did on your reading guide as well. So hopefully you're going, oh yeah, I remember this term. Yeah. So you can tell this is me. This is the way this is written. In the land of make-believe. Okay. So when you're talking about yield, usually, what do we call that thing in the middle between the reactants and the products? What do we call that arrow? The yield symbol, right? So we're talking about yielding products. So as that kind of sits in your brain, think about how you're referencing these problems. If it ever asks for oxygen or chlorine or something, you're like, well, which one? The one in the reactants or the one in the products? It's the one in the products it's referencing. So the yield of a product is probably one of the most important terms to underline there. In a reaction, well, if we were perfect chemists and perfect students and did our reactions under vacuums and no airflow and, you know, deionized water, 100% our water's tiny bit ionized, not 100% deionized, with perfect conditions, which I'm going to call that the land of make-believe, because, you know, we're human. We're just human. We don't always have those perfect conditions. We would get a certain amount of yield. We would get a certain amount of product. And we call that theoretical because theoretically, you know, push your glasses up, theoretically, we should get this amount of product if we do this perfectly. But that's not always the case. And so we do call that TY, theoretical yield, because we should be able to get that from a given amount of reactants that react. And that's what we think should happen. But then we get in the lab, and we get going, and then Mikhailo bumps my elbow, and I spill the reaction everywhere, and I scrape it off the table to try to not let Miss Enlow see, and then I put it back in there. I'm like, okay, we're still good. But some mistake has happened. Some human error has occurred. And we actually get the actual yield. Now, which of those do you think is going to be bigger? The theoretical yield or the actual yield? the theoretical. We should probably get quite a bit, or assuming 100% yield, we should be able to get what we thought we were going to get. But if we spilled something, we had some sort of mistake in the reaction, we probably got less than we thought we should. So many times, this is our lesser amount, and this is our greater amount in the end. Now, occasionally we might do a reaction, or we're supposed to heat it up and drive the water off and dehydrate it. But what if we don't dehydrate something on the way and there's a lot of water still embedded, like in our crystals or something that we're forming? Well, then our actual yield might be higher just because there's water weight involved. There's something contaminating it. So it's usually the lesser amount, but not always. It can have can be contaminated. Can be contaminated. I hope you guys can kind of see what I'm saying here. Okay, so this is what's physically reacting in the lab. Now, in a problem like this, I will tell you that the theoretical yield is going to be one that you have to calculate. And you're going to calculate it from stoichiometry, from your process that we were just doing with our balanced chemical equation, writing our dimensional analysis, canceling our units, and so forth. And the actual yield, this is going to be given in the problem because I'm giving you guys some context. Shut my door, Omar. Shut my door, Omar. Thank you. I'm giving you some context so whenever you're looking at a problem, you're like, which is which? This is how you know. Because I'm not going to be like, Ira, go do that lab real fast. I need this actual yield for the problem. I'm going to have to give that to you because you guys are going to get up in the middle of the class to go do the lab. But we will do a lab where we utilize this logic. Okay, so whenever you're calculating percent, just like always, you always do thing that you're looking at over the total times 100. Well, the thing we're looking at is what we get in the lab. Either we get it in the lab or it's given in the problem over our stoichiometry process or our stoichiometry calculation, which we're calling our theoretical yield, we should get in our reaction process. And every single time you always multiply by 100 because that's what our process of percent is. So this will give us percent yield. Okay, so if you were like a fantastic lab student, what's a really good yield, do you think, for a reaction? 99 would be great. It's hard to get, but yeah, 99% is good. What else is good? Okay, 100% is probably not going to happen, but unless you were perfect, okay? What else? What's probably a reasonable? 80%. I'm good with like 80% and higher because we all make mistakes. Now, if you're getting like 10% yield, don't quit your day job because it's not working out for you. So you want to make sure that your yields are really high, and so that gives you some perspective. You want high yields. Okay, so I have a joke for you, but it's actually in the next slide. Well, yeah. So, and this is from my AP Chem class because this is what they had to do because they got extra credit for getting the best percent yield in their reactions. They had a 3-day lab. Like, from a faucet purifying, percent yield, 9.63%.
Nice.
Because this was not good. Wah, wah, wah. Okay. And then lab grade based on percent yield, spend an hour pathetically scraping every last grain of product off the glassware table and floor. Because that did happen, because they did spill their stuff everywhere and it crystallized on the table. I was like, you better get that off the table, and they're scraping it off. I'm like, no worries about the purification, but you got your yield, so it was totally contaminated. But it was, we did purity testing too, so anyway, they did that. Who knows Miss Hayes, her son, Nathan Hayes? Ask him about it. Okay, so what's the percent yield? Okay, so here's our big question. It's our only question we're going to have time to do right now. What does this mean? Before I even read any further, what does percent yield calculation mean? Actual yield over theoretical times 100. Okay, so this is what we're looking for, right? Okay, when 14 grams of magnesium chlorate decomposes in 3 liters of the gas of collected STP from decomposition. Woo! Too much information at once. So break it down. When 14 grams of magnesium chlorate decomposes, what does this mean you're going to have to do? Decompose magnesium chlorate. How do metal chlorides decompose? Oxygen and metal chloride. You've memorized your decomposition reactions. Okay, so I'm going to go ahead and do that first before I even do the math. So what's magnesium chlorate? 3, 2, because magnesium's got a 2 plus charge. Crisscross, and then we're done. Oxygen, I heard, O2, and what else? Can you give me the full thing? MgCl2. Okay, balance? It's not balanced. Balance it for me. A 3 in front of oxygen. Does that satisfy?
Satisfies that.
Yes, and the chlorines are good and magnesium. Okay, good. So check, we've decomposed magnesium chloride. Now, I know that this is my given, and remember, that's our process of taking our given, getting to a yield. Okay. When 3 liters of the gas, cryptically I tell you the gas because I want you to put it to your products. What's the gas? Okay, so it's saying 3 liters of oxygen are collected. Key word is collected, right? What is that telling you?
Actually,
That is telling you actual yield. Put AY under there. That tells you actual yield. So we already have the numerator. So what do you think we have to find? The denominator. We have to find the theoretical yield, which I told you was done through stoichiometry, through the math process we've been doing. Okay, well, what do I have to start with then? 14, because that's my given of magnesium chlorate. Okay, I don't care about magnesium chlorate. I want to get 2 grams of what? I mean, not grams. I want to get to liters of oxygen. So I didn't mention this on the previous slide, but the units of yield must be the same for numerator and denominator to cancel out. And I think that was kind of obvious, but this is our actual yield. We're looking for a theoretical yield of liters of oxygen. That's our true question. So I've got grams of magnesium chlorate. What do I have to get to first? Moles, because moles gets me to everything else. So 1 mole of magnesium chlorate goes on top. And the molar mass, which I hope somebody can calculate, number. Anybody?
191.21.
191.21 is what I'm hearing. Sounds great. I'm doing this last step and then I'll have to back up. So moles of magnesium chlorate need to cancel, right? Remember, I'm looking for liters of oxygen. So what am I going between? What's my mole ratio? Wait, what's my mole ratio? 3 to 1, and then you go to liters. I'll finish this later. Go. Get out of here.